Okay, let's take a look at this copying machine again, which was originally purchased at $2,000 and it depreciates by $50 per year. Make a table of values that keeps track of the worth of the machine as years pass. Got it. So years old. Years old. How old is that machine? And its worth in dollars. If it is brand new, it is 0 years old and it is worth $2,000. If it's 1 year old, it depreciated by $50. If it's 2 years old, it just depreciated by $100. So it went down again by $50. So it's at $1,900 of worth. After 3 years have passed, now it's at $1,850 of worth because again it went down. What is the pattern in this table? Is it linear or exponential? Well, as mentioned previously, it keeps going down by 50, so it is linear. The pattern is a constant minus $50. Compute the slope. Well, remember that the slope is the change in the response variable as a ratio to the change in the explanatory variable. Okay, and I believe that the worth of the machine is responding to the how old it is, which is the explanatory variable or the independent variable. So time is independent and the value of the machine or the worth of the machine depends on knowing how old it is. So here we go, the change in response. Well, in the first year, the change in the response, the change in the worth was that it went down $50. So negative $50. And the change in the explanatory, 1 year. In 1 year, it went down $50. Okay, so there's our slope, if you wish. I prefer it with units, but negative 50 is technically correct too. Interpret the slope. Interpret what the slope means in the context of the situation. We can do that, especially when we write units on it. The units are very valuable. Interpret the slope. The worth of the machine goes down $50 each year. So the worth of the copier goes down by $50 each year that passes. Write an equation that describes the relationship between the value of the copy machine and the time passing. Now, I actually let my students struggle with each one of these, and the last one too, the cheap seats and the driving. So the majority of class time when I'm teaching this is that my students kind of sit there and they're like, what do I do? And I'm like, create something and see if it works. And then they kind of struggle through it, and then somebody in their group has this revelation. Well, it's not usually like a revelation. It's like they exchange ideas and their ideas get better and better and better as they talk through it. But I noticed that it's originally $2,000 and then I'm subtracting 50 however many times, and that's however many years pass. So to me, the worth, I'll call worth W, is equal to start at $2,000 and take away 50 T times, where T is how many years have gone by. So I better write that down, where W equals the worth in dollars and T equals how many years old it is. Okay, so it started being worth 2,000, and then 3 years later you had taken away 50 3 times because it depreciated by $50 per year. So I believe this will work, and if you don't trust me, you should plug in different T's and see if you get the right W's. What was the initial worth of the copying machine? $2,000. How did it show up in your equation? It lives right there. Before we start taking away our constant change, whether it's a subtraction or whether it's an addition, it's always the startup. So how did it show up in your equation? Always immediately after the equal as the start amount. Graph your equation, point to where this initial shows up. Okay, I'm going to do this by hand. And it looks like we need to go up to 2,000. And it would be nice if we could count by hundreds, but that would make us make ticky marks like 20 ticky marks. So it looks like I'm going to even have to count by 200s. Giving us 10 ticky marks. Okay, so okay. So on my vertical axis here, this is the dependent variable, or the response, and that is the worth of the copying machine in dollars. And the independent variable, or the explanatory variable, is going to be years old. Okay, and let's see. We'll go out to 10 years old. Yeah? All right, here we go. Let's see what we can do. It starts at 2,000 years old. So after 0 years old, it is worth $2,000. How about, okay, I think the best thing for me to do is this. This would be what, 1,200, 1,600, 1,800? It'll be worth 1,800 after 4 years. So, okay, after 4 years, it is worth $1,800. That means after 8 years, it goes down by 200 again. Okay, got it. And then 10 years, no, maybe it's better to do 12. Just because if it's going down $50 per 1 year, then it's going down $200 every 4 years. So extend this, perhaps there. Okay, I'll label that with a 12, and let's see, 200, 200 more, and then 200 more. Okay, so after 12 years, we're at, what are we at? So that would be 1,800, 1,600, and that would be 1,400, etc. Okay, so here is the graph of what's happening. Okay, trying to make a straight line, always tricky. Use a straight edge, please. And it says point to where the initial value shows up, right there. There is where the initial value of $200 shows up right there on the horizontal axis. So the initial worth or the initial value, the thing that comes immediately after the equals in our equations, is where it hits the horizontal. Darn it! For Pete's sake, that's not horizontal. Shenanigans on me. That would be a vertical line, my friends. Whoops! For a moment there, I forgot what was up and what was down and what was left and what was right. Vertical axes. All right. Let's make some remarks about this. Because hopefully by now you're picking up on a pattern where the slope-intercept form of a line, to me, looks like this. Let's write it like this. Response is equal to the initial, okay, plus or minus, by the way, so I'll put plus or minus, the constant change, or the ratio, or the slope, times the explanatory variable. Okay, that is, so here's what I mean. Bring it back, bring it back. The initial amount plus or minus that constant change, constant add or subtract, which is also, by the way, the slope, times the explanatory variable. In this case, it was time. Yeah? Okay. So, rewritten in terms of like textbook style, this would read y is equal to the initial, which is b, called the y-intercept, okay, plus or minus whatever. The constant change, of course, is the slope, as we know, because that constant change is actually the ratio of the change in the response to the change in the explanatory, which is also known as a ratio of change, which is also known as the rate of change, which is known as the slope. And then the explanatory variable is more commonly named x. So now let me rewrite it one more time. How you're taught it in textbooks is that this is mx plus b. Okay? And I need you to know that really these are all the same thing. The response is equal to the initial amount. B is the initial amount when the x is 0 or the t is 0 or the independent variable is 0. The explanatory variable is 0. So the initial amount and then plus or minus that constant rate of change times the explanatory variable because it happens that many times. So that rate, that constant increase or decrease happens that many times. Hence, where this equation comes from. So, let's make a few remarks about this. My first remark is exactly that. Okay. B is the initial amount, initial value of the response variable. In other words, the value of the output when we input 0. I don't know if we want to write that. I'm going to write it. The value of the output or response variable when the input is 0. And it's weird for me to use this input-output language because ultimately, when I think about this equation, I think, well, this constant change has been added 0 times initially. Initially, you haven't added or subtracted anything. So it's when when this explanatory variable is 0. Okay, so symbology-wise, symbols, B is the initial value of the response variable when the explanatory variable is 0. Okay, remark number 2, something else that is remarkable. The point 0b, or the coordinate pair 0b, is called the y-intercept. Okay, and that's because y is used to represent the response variable in general. Let's see, the point 0b is called the y-intercept because y equals the response. And that is put on the vertical axis. I think I can fit it in. There. Okay, so it's called the y-intercept because right here, the response variable is, there was a gnat, killed it. The response variable is put on the vertical axis, and that is also called the y because the y variable is known as the response variable. Okay, and the slope is the constant rate of change. So m is the slope the constant rate of change, which is also equal to the ratio between the variables and is equal to the same added amount every time. So m equals constant add or subtract amount every time and is also equal to the ratio of change. Yeah. Lots of synonyms running around, or rephrasing of the same business, or reinterpreting to fit the context of the situation. And I think that's why everyone gets lost. And that's because, I mean, we really do use all of these turn of phrases to just indicate the slope, and even m. And let's see. Another thing that is remarkable is that we just saw two scenarios. One where the m was positive and the price of the ticket was increasing, and one where the m was negative and the value of, or the worth of, a copy machine was going down or decreasing. So when m is positive, we see increases. When m is negative, because this is the constant rate of change, we see decreases or depreciation, going down. Okay, in the next video, we're actually going to do two different examples, pizza cost, and we're going to look at cost of snow cones as well, just to kind of pull all of these ideas together.